So for CCENT Chapter 7, we're going to talk about Layer 3, the network layer, where routing occurs, where IP addressing occurs, yes, where IPv6 addressing occurs, and so on. This is a fun chapter. It's a lot of information, and of course it is a precursor to what we're going to be talking about in the next chapter, which is more details on subnetting and IP addressing and so on. All right, so the network layer, as we talked about before, this is layer 3 of our OSI model, right? This is where routing occurs. This is where IP addressing occurs, IPv6 addressing, and in some cases some other types of addressing, but predominantly it's going to be IPv4 and IPv6. Routing is a very, very large topic, so we're not going to be talking about all of the routing concepts yet, but we will be talking about routing as we move forward through some of the future chapters. A couple of components about the network layer, or a couple things about the network layer that you need to understand before we move on. First of all, we know that there's an addressing component at the networking layer, right? Specifically IP address, source IP, destination IP, or source IPv6 address, destination IPv6 address. We also know that encapsulation occurs at this layer. Not at the same, in the same way that we saw at layer 2, where we had a header and a footer, but we have a header that contains information relevant to transporting information across the network. As we go through this chapter, we're going to detail what that header looks like. It's a little bit more complex than your Ethernet header that we saw before. All right? We know routing occurs at this layer, and de-encapsulation occurs at this layer as well as we go back up the protocol stack on the other side of the network. Two common network layer protocols that exist, IPv4 and IPv6. There were some older protocols that existed, AppleTalk, IPX, Internetwork Packet Exchange, and Connectionless Network Service, or CLNS, but these protocols have been deprecated, retired, and are no longer used. So our focus is going to be essentially on two different protocols, IPv4 and IPv6. And yes, we will spend a lot of time talking about IPv6, probably more than you want to. But I love IPv6. I think IPv6 is well, it's about time that we look at moving to IPv6. It's a lot of benefits to IPv6. Some of the characteristics of IP, first of all, connectionless. Now, what does it mean for a protocol to be connectionless? The other option would be the protocol is connection-oriented. But what does it mean for a protocol to be connectionless? It means that the sending host does not establish a channel or any kind of acknowledgement or handshake with the receiving host prior to sending the information. In other words, as a router or as a host sending a datagram, an IP datagram, I have no idea whether or not the person is actually there. Think of it kind of like mailing a letter, right? You can mail a letter with a delivery receipt, confirmation receipt, whatnot. That would be more considered connection-oriented because you know that the message is delivered, you know it was delivered to the right person, etc. You got an acknowledgement that that message was delivered. Sending a mail or a piece of mail through the mail system without any kind of confirmation is kind of like connectionless. You really don't have any idea that the message is being delivered. All right? Now, that's post-delivery, but when we talk about connectionless, we typically refer to it in the terms of pre-delivery. In other words, we don't establish a session or identify that the receiving host is even online or available to receive data. In addition, IP is best effort, meaning that there are no acknowledgments for delivery of datagrams, there are no sequence numbers for delivery of datagrams, and there's no way to guarantee that packet delivery. We rely, specifically IP relies on the upper layer protocols to handle that kind of information, namely TCPs. Remember, what layer does TCP operate at? Layer 4. Agreed? Whereas IP operates at layer 3. Also, IP is completely media independent. It operates independently of the physical layer. The reason why they mention this specifically at this layer is because certain protocols at layer 2 function differently depending on the physical layer construction. Whereas IP doesn't care if it's twisted pair Ethernet, fiber, wireless, all of the transmissions are the same. Does that make sense? So the physical layer is irrelevant when it comes to IP. Now we spent some time in chapter number 3, I think it was chapter number 3, talking about the data link layer, right? And one of the things that we learned about the data link layer was essentially how frames were formatted. In other words, like an Ethernet 2 frame has destination MAC address, then it has source MAC address, then it has type field, then it has the data field, then it has the FCS. Well, guess what? This is an IP datagram. It's a little bit more complex than your standard Ethernet frame, right? Actually, a lot more complex, isn't it? But guess what? We're going to go through every one of these fields, and we're going to talk about what each one of these fields represent. But before we get into that, let me explain to you how you read this information. You read it like a sentence in a book. The overall size of an IP datagram is, an IP header, normal IP header is 20 bytes. So the total amount of information contained in an IP header is 20 bytes. You read the lines from left to right. So this is the first byte, second byte, third byte, fourth byte, fifth byte, sixth byte, seventh byte, eighth byte, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Does that make sense? Mm-hmm. All right?
4 and 5 lines.
Yep, 4 bytes for each line and five rows. Okay? Now, obviously, this is not what a header looks like in the real world. A header looks like a string of ones and zeros. But obviously, if we were to write it out across the screen, it would be so small you wouldn't be able to read it, right? So we tend to write it this way. The first nibble, which is half a byte, the first nibble is the version. Quite simply, this field tells us what version of IP we're running. There's only 2 versions that you have. If it's IPv4, the value of that field is going to be 0100. If it's IPv6, 0110. Does that make sense? Those are the binary equivalents to 4 and 6. You guys remember the scale? Here's the scale. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. This is 1 in decimal, 2 in decimal, 4 in decimal, 8 in decimal. IPv4 is that. IPv6 is that. 4 plus 2 is 6, right? All right? So that's a very simple field to understand. The version represents the version of IP. Simple. The second field is a little bit more complicated, not fundamentally in what it's supposed to do. It's called the IHL, IP header length field. Anytime you see an IHL or a header length field in any header, it means that the header can change in size. This particular header can be 20 bytes, but you can see down here we have some options and some padding, so I can go above 20 bytes if necessary. So actually, an IP header is variable in length.
Is there a maximum?
There is a maximum. Typically, it's going to be 40 bytes. You're not really going to go above 40 bytes because the options that you need to include are not unlimited. There's a limited number of options that you can include. All right? So the header length tells us if the header is 20 bytes, if it's 30 bytes, if it's 40 bytes, or whatever. All right? So far, so good. The second byte in the past, this was called the toss byte. How do you represent, we have a question here online, how do you represent 20 bytes with 4 bits? Well, we don't represent it as a decimal number. He's saying, if this field is only 4 bits, how can I actually say that the header is 20 bytes? It's a setting, right? If you see a binary representation of that field, that represents a header size. It's not an actual conversion from binary to decimal, because there's no way to represent 20 bytes with 4 bits if you're doing a direct binary to decimal conversion. All right? So it's not exactly that way. It is a binary representation that represents certain values. I'm sure that there's a mathematical calculation involved in that process as well. All right? The next byte that you see is called the toss byte. The toss byte. Any idea what toss stands for? Type of service. Type of service. Okay? Now, this is a little bit confusing, and we're not going to get into the details here, but essentially, that byte, this toss byte, is used for QoS marking. Okay? Now, QoS is a way for us to prioritize traffic based on policy. Some traffic gets routed or switched faster than others. Some traffic gets policed. Some traffic gets shaped. Some traffic goes into a priority queue. Some traffic goes into a class-based weighted fair queue, whatever. But in order for us to apply a policy to traffic, say the traffic is coming to the router. The router itself has a QoS policy defined. 99% of the time, that policy is enacted based on identifying the type of traffic coming into the interface, which is where that marking comes into play. This is an 8-bit field, which means we have 8 bits to mark the packet. In the past, we didn't use all 8 bits. In the past, we only used 3 bits. Okay? So we had 5 bits that were fixed. Oops, 4 bits that were, 5 bits that were fixed, right? And then we had 3 bits that we could use to specify the class of service. Which means that I had, as far as toss goes, I had 0 through 7. Oops. Let me get rid of my 0 here. All right? And if the traffic was getting marked as 7, it would be a 111. 6 would be 110. 5 would be 101. 4 would be 100. 3 would be 011. 2 would be 010. 1 would be 001. And 0 would be 000. Now, what would be the point of marking a packet with one of those values? Why would I mark a packet with a value? Because I use that marking to apply a policy to that packet. It's like saying, You go to a theme park, and you can buy a wristband that puts you at the front of the line. That's your marking.
So I say differentiated service.
Well, differentiated services is an extension of TOS. The problem with the type of service field is that we were limited to only 8 classes of service. We can only identify 8 variants of service. Okay? So what they did is they said, let's go ahead and revamp this field. Well, why are we wasting all these bits, these 5 bits? Why don't we go ahead and expand this marking capability? So they came up with something called the Differentiated Services Code Point. Now, the scope of DSCP is beyond this class, for sure. You can learn about DSCP in QoS classes and whatnot. I'm going to give you a brief description of it, but it really can be rather advanced. There are a lot of components in DSCP marking. But let's go ahead and talk about this from a kind of a general standpoint. So if you look at the byte here, it's actually divided into 2 pieces. You've got your DSCP marking, and then you've got this thing called explicit congestion notification. Let's go ahead and forget that that's there, not talk about that. But the ECN bits are 2 bits. So that means how many bits am I using for DSCP? 6. Which means I haven't just doubled the number of markings that I have because it's powers of 2. I've actually significantly increased the number of markings that I have. But it's not quite 6, and here's why. In that DSCP field, all right, DSCP stands for Differentiated Services Code Point. We have essentially 2 sections, well, 3 sections actually, in that DSCP field. If you were to break it down to its smaller components, this is what it would have. You'd have a class selector field, you would have a DD field, which is drop discard, and then you would have, well, we'll just call that X because that number is always 0. All right, now the class selector field is always 3 bits. The drop discard, or discard, well, DD field is always 2 bits. So you have 5 bits for marking. DSCP of best effort. That's not hexadecimal, by the way. That's best effort, has a marking of 0, 0, 0, 0, 0, 0. 0, 0, 0, 0, 0, 0, 0. So that's the lowest class of service that you can have. Then we have another DSCP marking called EF, expedited forwarding, which is another class that's defined. And by the way, you don't need to know any of this for the exam. I'm giving you additional information just so you can get kind of a little bit of exposure to DSCP. EF is going to be 101110. And then you have these things called assured forwarding classes, and then you have class selector classes, and then you have stuff above that expedited forwarding. What's the difference here? The difference is we just have more granularity. So instead of being able to classify only 8 different classes, I can classify, well, essentially 32 different classes. If you do the math, you have 5 bits that you can play with. That's 32 different classes that you can specify. Now you might see this written a couple of different ways. So let me give you an example. DSCP EF is also equal to 46. All right? 46? I think it's 46. We'll find out here in a second. Why is that? Well, because the field is 101110. Now, if I put this on a binary scale, 1, 2, 4, 8, 16, 32, 32 and 8 is 40, plus 4 and 2 is 46. So DSCP-EF is actually a DSCP value of 46. EF is just the class. It's a predefined class, expedited forwarding. 46 is the actual DSCP number, right? DSCP best effort equals 0, 0, or just 0, because all the bits are 0. All right? So what's the bottom line here? This field here, actually the whole byte, is used for QoS. All right? Any discussion beyond that, we really have to get into some heavy-duty talking about QoS, so I'm not going to get into that. But that's what that field is for. Okay? The total length field, it is a 16-byte field. 16-bit, excuse me. 16-bit field, which is, by the way, that's called a word. Right? A byte is, or 8 bits is a byte, 16 bits is a word, and 4 bits is a nibble. All right? What is the total length field? Basically, it tells me how much information is being carried inside of IP. The total length equals the length of my header plus the length of the data that's being encapsulated. So if I see 700 bytes there, a total length of 700, and I'm using a normal IP header, I know that I am carrying above layer 3. Above layer 3, I am carrying 680 bytes of information. Very, very simple field. It just simply represents the amount of information that's being carried inside of the datagram. Now the next 3 fields here, identification, flag, and fragment offset. Well, the flag field has several meanings, but identification, flag, and fragment offset, these fields are used for in the event that packet fragmentation has to occur. Remember what fragmentation is? Fragmentation is the concept of dividing data up into smaller pieces, but at layer 3, not at layer 4. So if fragmentation is occurring, certain values get placed into these fields to identify those fragments so that we can put those fragments back together at the other side of the connection. I'm not going to get into the details of those fields, but that's fundamentally what those fields represent. Time to live. This is an interesting field because it plays a big role in a lot of functions that we run inside of our network. How many bits is that field? 8 bits. Right? That field is 8 bits. So it's a byte. What is it for? Well, it essentially allows us to identify, excuse me, it allows us to identify the lifetime of a packet. What do I mean by that?
Is that expression?
Mm-hmm. Let me explain how this field works. When a device generates a datagram, it seeds or sets a value into that field. And depending on the type of device will depend on what that value is. But let's say it's the maximum. What is the maximum number I can put into that field?
8 bits.
Well, it's 8 bits, but from a decimal standpoint, what does that mean? What's the maximum number I can put into that field? 255, right. And the minimum number I can put in that field is 0. All right? So I'm a computer, I'm generating a datagram, right? I'm generating a datagram. Let's generate a datagram here. I'm sending out a datagram with a TTL value of 255. Every single time that datagram goes through a router, that TTL value gets decremented by 1. All right? So here I am. I've got my PC. I've generated a datagram. It has an initial TTL of 255. I send that through that router. I send it through this router. I send it through this router. When the packet traverses this router, it's now 254. When it traverses this router, it's now 253. When it traverses this router, it's now 252, and so on. You get the idea, right? What happens when that TTL value reaches 0? The message gets dropped by whomever is setting that value to 0. 19 is not the default. It depends on the host. Cisco routers generate datagrams with a TTL value of 255. Windows machines generate TTL values of 128, I believe. But it does depend on the operating system. Whatever the value is initially, the end result is the same. You can only go through as many routers as are available before that number reaches 0. But once that number reaches 0, that datagram can no longer exist. This TTL value was put in as a loop avoidance mechanism for the internet. So if a packet gets caught in a loop somewhere, it doesn't just endlessly rotate around that loop, taking up all of the bandwidth and whatnot. After a certain period of time, the packet goes away. Which, by the way, means that if the hop or if the destination is more than 255 hops away, you can never get to it. You were going to ask questions, sir. Go ahead.
Oh, yeah, I was going to say, so it only decreases the value when it's going through routers?
Yes.
It never goes through a switch. It just passes there on time.
So the question is, it only decreases the value when you're going through routers, but it doesn't decrease the value going through a switch. That is correct. Why would it not decrease the value going through a switch?
Because the switch doesn't get like the average line.
That's right. Switches are layer 2. Switch never looks at this stuff. This is layer 3. Switches operate at layer 2. So as far as the switch is concerned, this is just data. Does that make sense? All right. Now, here's an interesting concept. Pull up my command prompt here. And let me just do a, uh-oh, what should he go away? There we go. Let me just do a quick trace route to cisco.com. Traceroute is a tool, we'll see this again later on, but traceroute is a tool that allows me to identify all of the routers that I'm going through to reach a particular destination. Now, it may be blocked from here, I'm not sure. Looks like it might be blocked from here. But how does traceroute work? Guess what? All traceroute is an ICMP echo request, a ping, where the time to live is being manipulated. Let me show you. So PC, I do a trace route over to X, okay? And to get to X, I go through this router, I go through this router, I go through this router, and I go through this router. Now I do a trace route to X. What happens? The PC generates an ICMP echo 3 times. But it sets the TTL for that initial echo to 1. So when the ping is to X, but the time to live is 1. So when this router wants to forward the ping, it says, oh, wait a second, I just decremented the time to live to 0, and it sends a message back to the host saying, I just killed your packet. Well, technically it's called time to live exceeded. In that response, guess what I just discovered? I just discovered the first router. So then what do? I send 3 more ICMP echoes with a time to live of 2. It goes through the first router, goes down to 1, goes through the second router, it goes to 0. Then this router sends a message back saying, I just killed your packet. And now I'm able to identify that router in the path. That's how traceroute works. It's simply an ICMP echo request in which we're manipulating the time to live field.
Well, if a packet arrives at a router and its time to live is 1 when it arrives at the router, and the destination is attached to the host connected to that router, is it discarded or is it
It's still discarded. The only time the time to live is decremented is if the packet has to go through the router. Well, coming in one interface and going out another interface, whether that network is attached to that router or not, is still a hop. Does that make sense?
Yeah.
It's still a hop. The time to live, the only time that the time to live is not decremented is if, say for your example, you've got router, and you're doing a trace route to the inside interface of that router, or the closer interface, right? So let's say I start with a TTL of 10, here it becomes 9, here it becomes 8, but it doesn't go to 7 because it didn't go through the router.
Because that was the destination.
That's the destination of my trace route. All right. All right. Protocol. The protocol field is to layer 3, like the type field was to layer 2. Well, what did the type field do in layer 2? What does the type field do in layer 2? We had destination MAC, source MAC. Trust me, we are just beginning here, guys. So destination MAC, source MAC, type field, data, and frame check sequence. Does that look familiar? This is my Ethernet 2 frame, right? Destination MAC, we know. That's where the frame is going to. Source MAC, that's where the frame is coming from. What was that type field used for? It tells you what is happening at layer 3. What is being carried inside of the frame? Is it IP at the next layer? Is it IPv6? Is it ARP? Is it ICMP? Whatever. This is a hexadecimal field, well, it's a 2-byte field, that allows me to identify what's happening at the next layer. Well, guess what? The protocol field allows me to identify what's being encapsulated inside of IP. If it's TCP, it's protocol 6. If it's UDP, it's protocol 17. If it's EIGRP, protocol 88. If it's OSPF, 89. If it's ICMP 1, et cetera, et cetera. So the protocol field essentially just tells me what's being carried inside of IP. Just like the type field at layer 2 tells me what's being carried inside the payload, inside the frame, the protocol field allows me to identify what's being carried inside of IP. I know it seems like a lot of information. All right? It is a lot of information, but This can be useful information because if you're doing a Wireshark capture or you're troubleshooting communications, understanding how these frames are formatted, how the packets are formatted, how the segments are formatted, gives you a better understanding of how devices communicate. All right, we only have one more field really, because I think you guys know what these two fields do. Right? Those are pretty obvious, 32 bits each, source IP, destination IP. So we have this checksum field. This is a hash, pretty much like a CRC, just like at layer 2. Routers or devices that talk layer 3 generate a checksum based on the header information and some of the payload information. That information gets sent across the network, and every router that receives all of this information here, right, does the same calculation, verifies the validity of the checksum. If the checksum matches, then the packet header is intact and the information is not corrupted. It's an error discovery mechanism. It's also kind of an integrity checking mechanism, isn't it? Because if somebody is modifying information midstream, the checksum will fail unless they're replacing the checksum. There's no authentication function to it, so it could easily be replaced. So that's our v4 packet header. What does that look like in Wireshark? Well, looks like this. We have a question online, what would happen if the checksum failed? Right? If the checksum fails, the packet gets dropped. Just like in the frame, if the CRC fails in the frame gets dropped. So here's a representation of a packet that was captured in Wireshark. We've already talked about what happens at layer 2, right? So here's my layer 2 header. We're done with that. It's not even expanded here, so we can't really see it. This first row here just is what Wireshark puts in there to identify information about the PDU that's been captured. But here's my layer 3 information. That is my header. Okay? What version of IP am I running? I'm running version 4, right? Is this a standard v4 header or is this an extended v4 header? Standard, it's 20 bytes. Does this packet have a QoS marking? Here are those 6 bits I was talking about for DSCP. They're all set to 0, which means no QoS marking. Oops. The ECN bits are also not set. We didn't really talk about those 2 bits, but it's not important right now. The total link field. What does that tell me? What does the total link field tell me? It's right. How much information is carried inside of IP, including the header itself. So I know that I have 46 bytes of payload because the header is 20 bytes. Does that make sense? Identification field, fragment or flag field, don't fragment, fragment offset. Here's our time to live, 128. All right. Protocol. Wireshark is nice because it takes the binary values and it converts it to a nice readable output. The protocol is TCP. So what does that mean when it says protocol TCP? It means that the next header is a TCP header. You know what I'm saying? If it was protocol 88, then that would tell whoever's processing this datagram that the next header is EIGRP. If it was protocol 89, the next header is OSPF. If it's protocol 1, the next header is ICMP, and so on. And then we have our checksum, and we have our source and destination IP address. And then we get into layer 4. We'll talk about layer 4 later. There's my layer 4 stuff at the bottom. So when you break down each layer and you identify how these headers are formatted, looking at this information in Wireshark becomes a lot easier to understand. Now, there's a difference between understanding what the fields represent and being able to interpret how those fields translate to a problem or whatever. But let me give you an example. Let's say you're running voice in your network and you have some concerns about whether or not the voice packets are being marked correctly. Well, that's very simple. You do a Wireshark capture, you look at the differentiated services code point for those markings. Because you know that the traffic is going to be treated differently if it's not marked. Here's another thing. This flag right here, don't fragment. Any idea what that means? We didn't talk about that, but any idea what that might mean?
Do not break down or separate the message.
That's right. At layer 3, not layer 4, segmentation is layer 4, but at layer 3, if the packet needs to be broken down into smaller pieces because of an NTU, it won't happen. What's going to happen instead? The packet gets dropped. Yeah. So if a router is processing this datagram, and let's say that my MTU, it would never be this, but let's say my MTU is 20 bytes. I already know that I'm exceeding that MTU value by 20 bytes, right? Or by 26 bytes, because I have 46 bytes of payload. So the router that's processing this datagram would simply drop it. Because I can't fragment it. The person who sent this datagram said, don't fragment. So if I can't fragment, I can't just send it over the wire exceeding the MTU, so my only choice is to drop it. All right? What about IPv6? Well, I think everybody pretty much has a good understanding about the fact that IPv6 provides a lot more address space, right? And actually, a lot of times when people consider IPv6, that's usually what they think about when they think about the benefit of IPv6. They say, oh, well, yeah, it gets more address space. But if I don't need no more address space, then I don't really need IPv6. But actually, IPv6 has a lot of features built into it that make it much more efficient than IPv4. First of all, the header is much more efficient. Believe it or not, the IPv6 header is less complex than an IPv4 header. 6 different fields have been removed in the IPv6 header that we have in the IPv4 header. Additionally, the IPv6 header is fixed in length. It's not variable. And when you're processing data in a network, anything that's fixed in length that is predictable is usually going to be processed more efficiently. Here's an interesting concept, right? The third bullet point down. No need for NAT. And that is because every IPv6 address is public. Now, that's not to say that there isn't a concept for private addressing in IPv6. Private addressing means addresses that are usable, but they're not routable on the internet. That was never intended to be something built into IP, this concept of private addressing. It was put into place as a stopgap measure for running out of address space. But it wasn't intended. In fact, a lot of applications had a hard time dealing with this concept of network address translation. By the way, does anybody know when IPv6 became a standard? Early last year? 1996, IPv6 became a standard. Right? It's been around for a long time.
I don't know why you're like it. Same year as your graduation.
Yeah, same year as my graduation, yeah. But it's been around for a long time. The reason why in the United States we haven't seen it too much is because 75% of all the globally routed IPv4 address space is in the United States, right? A lot of other countries, though, are implementing IPv6. And IPv6 has been implemented pretty much throughout the United States now. If you have AT&T or Comcast or Verizon, you're going to get an IPv6 address. Even the thinQtank web servers are IPv6 enabled. So you can access our servers through IPv6 or IPv4. So it's not that it hasn't been around, it just hasn't been widely adopted. Hopefully after our discussion through the rest of today and after lunch, you guys will be a little bit more excited about maybe implementing IPv6. So I digress a little bit, but anyway, they decided that with IPv6, because of the amount of address space, which you can see down here, it's pretty significant. Because of the amount of address space, let's go ahead and eliminate this concept of private addressing. Because really, the networks weren't really designed to work with private addressing. Network address translation just adds another level of complexity, another point of failure in the network, and another processing component which slows down the communication. So whenever you see this concept of global routing with IPv6, it just simply means that all IPv6 addresses are public. You have to put a little asterisk next to that statement, though, because there are some definitions for private addressing in IPv6. Generally, the question I get when I say this, though, all addresses are public, is they say, well, then that means that my hosts are vulnerable because they're routable, right? I mean, think about it now. Somebody wants to attack your PC inside your network, it becomes difficult, doesn't it? Because your PC has a private address. And the only way you can establish a connection to that PC is if that connection was already pre-established from the PC. Well, if the address is public, then you lose that functionality, right? Or that protection. But the reality is you're still doing everything that you should be doing anyway to protect your host. You still have a firewall on your network. You still have intrusion prevention and intrusion detection. You still have antivirus applications. You still have anti-malware applications. So you're still protecting your host from the rest of the world. You don't just simply leave your host out there to be wide open to the rest of the space. Okay? So the argument can be stated is that if you're doing security correctly, the fact that you're public or private makes no difference. I would have absolutely no issue putting a public IPv6 address on my host at my home because I know that my home is protected with security, with firewalls, with access rules, and so on. My PC is protected with a firewall, all right? In fact, I don't know, I would almost argue that by having a NAT boundary, you're making yourself more vulnerable to things like denial of service attacks and other types of attacks because somebody can just attack that edge device. Anyway, integrated security, this is an interesting concept. I don't know why it keeps doing that. My pen keeps switching off, I don't know why. Integrated security. IPsec is built into the protocol. So if two IPv6 clients want to establish an encrypted session between each other, they can do it directly with the protocol without the use of a firewall or a VPN client or some sort of security negotiation between you know, a thin client or whatnot. This is a great feature, and it's actually a mandatory feature in IPv6, meaning that it is a standard feature. Mandatory doesn't mean that you have to run it. It just means that every implementation of IPv6 has to support that function. Do you guys see a potential problem with that? The ability for two clients to secure their communication channel without the use of any kind of third-party product or third-party component, or even an integrated component in the desktop? Absolutely, especially in corporate networks. In corporate networks, a lot of corporations like to analyze traffic. They like to look at traffic. They like to sniff traffic to protect the network from intrusions or attacks. Well, if the traffic is encrypted, all of a sudden that becomes very difficult. So even though it is a mandatory feature of IPv6, in other words, it has to exist, it doesn't have to be used, you can disallow packets on your network that use this extension. You can't stop them from using the extension, but you can stop routing the packets that have the extension enabled, if that makes sense. No more broadcasting in IPv6. Not really, not technically anyway. No more broadcasting in the traditional sense, but we do have the ability to send data to all IPv6 hosts using the FF02:1 address, which is the all IPv6 host address. So there is kind of it's not directly broadcasting, but there is a way to communicate to all IPv6 hosts at once. All right? So let's do our little side-by-side comparison here of our v4 header and our v6 header. See all the red fields on the left? They're all gone. No header length field because the v6 header is fixed in length, 40 bytes. The other interesting concept is no identification flag or fragment offset, because packet fragmentation is not allowed in IPv6. Routers are not allowed to divide data up into smaller pieces. Only the sending host can divide the data up at layer 4. So fragmentation doesn't occur anymore. That brings in new challenges. For example, the MTU, the minimum MTU size on IPv6 is now 1280 bytes instead of 46 bytes. And we have something called ICMP MTU path discovery, which allows us to identify the MTU along the path from the host perspective. A little bit beyond the scope of what we're talking about here. The checksum's gone. Hey, if we're doing checksums at layer 2, and we have checksums at layer 4, why do I need a checksum at layer 3? All I'm doing is adding more overhead to the processing. So we're no longer checking every packet for its validity at layer 3. And of course, the options in padding go away because we don't have a variable length header. It's a fixed header. Now there is the blue fields here. These represent the fields that were simply just renamed. So traffic class is type of service. Payload length is total length. Next header is protocol. Makes sense. Hop limit, well, that's a good name. It's better than time to live, because hop limit is how many hops can I go through to reach a destination. Why was it called time to limit or time to live originally? It was called time to live originally because it used to be a time stamp. The problem with the time stamp, though, is that everybody's clocks had to be synchronized, and if there was a difference in clock settings, then the time stamp would not be valid. There's only one new field that was introduced. It's a 20-bit field called the flow label field. Now, you can read lots of documents online about what the flow label field is used for, and there are some kind of contradicting representations of that, but the idea is that it allows us to identify packets in a flow of packets. In other words, we can associate packet 1 to packet 2 to packet 3, which normally we wouldn't be able to do. Every packet is treated independently in IPv4. So this provides additional control mechanisms and additional ways for us to control those datagrams as they go through our network. All right? Here's our IPv6 header in Wireshark. It's no different than what we saw with v4. You've got your version field, you've got your traffic class, your flow label, your payload length. In this case, we have something called an extension header. That's another interesting concept. Let me go back and explain extension headers. This is a very, very interesting concept with IPv6. The ability to put the extension header. In IPv4, if we wanted to customize what IPv4's function was, we would have to use these option fields to do that. But we were limited to what we could customize. With IPv6, what they decided to do is they said, okay, if you want to add things like IPsec or source routing or other functions into IPv6, let's go ahead and keep the original header intact. But let's add a secondary header called an extension header. And by the way, I can add another header if I need to, and another header if I need to perform different functions. So the main header stays the same. The extension headers are customized, which means that we can essentially customize IPv6 to do whatever we want it to do. Keep in mind, as you add those extension headers, though, you're taking away payload space. But all right, let's see here. This is one of. Let's see. What are some of the reasons the MTU would change? That's a good question. And I don't know that I have a good answer for that, other than, well, one of the reasons is they wanted to avoid the need. Well, let me actually, let me explain my answer. I think that's what you're asking, but maybe you're asking something different. But they wanted to get rid of the need to divide data up at layer 3 along the path, where you would have serial links and Ethernet links and wireless links all running different MTU sizes. And it has to do with the way that the data gets framed and people sharing those resources using some sort of time division multiplexing scheme or some sort of transmission scheme or encoding method, right? That's why MTUs change in general. But when they defined IPv6, they said, hey, if you're going to support IPv6, you have to have a minimum MTU of 1280 bytes. Which means that if you set your MTU on your PC to 1280 bytes, then you'll never fragment. You'll never have, well, you'll always have to fragment, because we're going to always be sending stuff larger than 1280 bytes. But along the path, you know that you're never going to have an issue with that data being passed along the path. In other words, they were kind of trying to standardize this MTU setting, because in the past it was different. Now, Daryl, I don't know if that really answers your question. Probably doesn't, but that's the answer I'm going with. All right? And the idea with IPv6 is try to make it more efficient. Try to make it more efficient. All right? All right. So this is a good place to pause. We're not close to finishing this chapter, so it's getting into our lunchtime. So we're going to go ahead and pause the recording and head out to lunch. When it comes to layer 3, of course, we know another component of layer 3 is a function of routing. And routing really is just the process of getting data moved from one layer 3 network to another layer 3 network. This network that we see here, actually, we're going to be building in Packet Tracer. We're going to be setting up this network. We're going to be using this network to configure static routing. We're going to be using this network to configure RIP. And then we're going to move on to some other routing concepts tomorrow. But a little bit later on, we'll be setting up this topology here. But let's talk about what a router does. We know that routers operate at layer 3 of the OSI model. So they make their decisions on forwarding information based on information contained in the layer 3 header. Specifically, the destination IP address. It's not that the router can't read the other components of a layer 3 header, but primarily its decision on how data gets sent is based on the destination IP. All right? Now, the other concept that I think is extremely important to understand when it comes to routing, and by the way, this is any vendor, any environment, routers essentially have one goal. And that goal is to get the packet towards its destination by sending the packet to the next router along the path. All right? Now, I want to make that very clear, so I'm going to say it again. The goal of a router is not to figure out the entire path. It may be aware of the entire path, but the goal of every router is to get a packet to the next router. We refer to that next router as the next hop. All right? So you see we've got essentially 5 networks in this topology. We've got the 192.168.10.0 subnet. We've got the 192.168.11.0 subnet. We've got the 10.1.1.0 subnet on the right and the 10.1.2.0 subnet on the right. And then connecting the routers in between, we have the 209.165.200.224 subnet. All right? So if a host in the 10.0 subnet wants to reach a host in the 10.1.1.0 subnet, the host over on the left side, let me turn on my pen here, the host over on the left side is going to send its packet to its gateway. Hold on one second. There we go. The host connected over here is going to send its packet to its gateway. In turn, this router, it has a database on it called the routing table, and inside that routing table, it has an entry for the 10.1.1.0 subnet. So it's going to say, well, I need to send the packet to this router, and then this router is going to make a decision to send the packet to that switch or to the host connected to that switch, and then eventually to the PC that we're talking to on the right side of the network. All right? Once a router has made a forwarding decision, its job is done. In other words, once the packet leaves router 1 and goes to router 2, router 1's responsibility for that packet no longer exists. It's up to router 2 then to ensure that that packet reaches its final destination. So fundamentally, whether it's static routing, EIGRP, OSPF, BGP, ISIS, doesn't matter what the routing protocol is. The ultimate goal of any routing protocol is to identify a routing process, is to identify where do I send the packet to next. Very, very important concept. Now, routers, by default, don't really know anything. Out of the box, routers really have no knowledge of what's happening on the network. So routers have to be configured with IP addresses on their interfaces. The interfaces have to be activated, and for certain types of destinations, the router has to be told how to reach those particular destinations. So let's say I've got router 1, and you guys are going to be doing this, so it's very important that you follow along on this, but I've got router 1 here. I pull it out of the box. What's my first task? Well, my first task is to configure an IP address on each of those interfaces, and then to turn those interfaces on. All right, and of course, we're going to do that as a group in a little bit. So I configure an IP address on each interface. I turn the interfaces on. Now, something very interesting happens from that point forward. This router now has a routing table. And what goes into that routing table are what we call our C routes. C routes. C stands for connected. So what is a connected route? A connected route on a router is any network that's attached to that router directly. Does that make sense? All right, that doesn't quite look like a C, but there, that's better. All right. Now we'll see more about this in detail as we get into the routing sections, but the connected routes have to exist before any other routing can take place. What's interesting about those connected routes, though, is you don't actually have to program them. Simply by putting IP addresses on the interfaces and making sure that those interfaces are turned on makes those routes show up. So how many connected routes would be in router 1 if everything is working? Oh, 3, right. So I would have C, C, C. What about on router 2? 3, C, C, C. So router 2 is going to be aware of these networks. Router 1 is going to be aware of these networks. And by the way, router 2 and router 1 happen to share a common subnet. So they can talk to each other because they're directly connected to each other. But what does R1 not know about? Right. What do I do about these two networks? From R1's perspective, R1 doesn't know that they exist. The same thing for R2. R2 doesn't know that those networks exist. And that's where routing comes into play. Routing and from the sense of configuring a device to understand how to reach a destination. We can use static routes, we can use a default route, or we can use a dynamic routing process. All of which we're going to learn about over the next few hours. We've got 4 hours left today, so we got lots of time to go through lots and lots of interesting stuff. This second half of day 2 is probably one of the more interesting discussions that you'll see, okay? So routing is all about being able to carry or transport a datagram from its source to its destination. Routers don't know anything by default. What does a switch do when it doesn't know how to reach a destination? What does a switch do when it doesn't know how to reach a destination? It floods, right? It floods the information out of every port except for the port it came in on. What does a router do when it doesn't know how to reach a destination? It drops it. Routers only do what you tell them to do. All right? If they don't have knowledge about a particular destination, then they will not route the packet. So we're talking about a completely different mindset for a router. All right? All right. We'll learn more about how to set up those routes a little bit later on. So the goal of a router is, like I said, take information into the ingress interface. This is what we call an ingress interface, going in. Look at the routing information, specifically in the layer 3 header. Look at the destination IP, and then route that traffic out of an egress interface. Egress meaning leaving the router or exiting the router. Terms ingress and egress are terms that we'll see a lot later on, so it's important we understand that. All right? What's interesting, though, is that even though we have the entire stack here being transported, the router only cares about layer 3. That's it. Router doesn't care about what's happening at layer 4. It doesn't care about what's happening at layer 5, 6, or 7.
So simply, if we convert it to language, routers only read language number layer 3.
That's right.
Does not understand the evidence, but does not drop anything over to send it as it is. Only take whatever portion that we understand from the packet.
That's right. The packet header is the only thing that the router is concerned with. And fundamentally, only one field within that packet header, the destination address field. Routers don't route based on where the traffic came from. Routers route based on where the traffic is going to. Now, there are exceptions to the rule, right? There's this thing called source routing, and there are other policy-based routing features that you can implement that override the default behavior of what a router does. But for this class, all we concern ourselves with is the basic concept of routing. All right? Not advanced routing concepts like policy-based routing and so on. Please, sir, can you repeat what other people in your room say because we can't hear? All right? Basically, they were just reiterating what I was saying, which is that routers only care about what's happening at layer 3. That's it. Routers only care about what's happening at layer 3. All right? So let's go through a process that I think will be very useful for you guys. It is a process that we call the packet delivery process. Essentially, what we're going to do is we're going to walk through this concept of how data travels across a network and what happens to that information as it goes from router to router to router. So in this particular example, we've got PC1 that wants to send data to PC2. Now, we're going to go ahead and make the assumption that ARP has already done its thing and all the MAC addresses are known. All right, because if you add ARP on top of this, it can get rather complicated because we're adding additional steps along the way. But, so let's assume that everybody knows the MAC addresses and so on. If you look at the source IP address of the packet, it is 1.10, which is PC1. The destination IP of the packet is 4.10, which is PC number 2. Make sense? That's where we're going to, and that's where we're going from. Everything else above that, that's all just my data, all right? This is all just my data. This is my layer 2 footer. This is my layer 2 header, the white part here. So here's my layer 2, and then here's my layer 3, okay? But look at the source MAC address of the frame as it leaves PC number 2. The source MAC is 0A10, which is PC1. That makes sense, doesn't it? But look at the destination MAC address. The destination MAC address is not 0B20.
Oh, because it reads, this is a layer 2, and it reads the router.
Right. This is layer 2, which means that layer 2's reachability stops at the layer 3 device. So in order to reach PC2, PC1 says, I have to go to my gateway. So instead, it uses the destination MAC address of its gateway, which is 0010. And we know from our previous discussions, if PC1 doesn't know the MAC address of the gateway, it's going to do an ARP request. It's going to send out an address resolution protocol request to discover the MAC address of the default gateway. All right, great. So that frame makes its way over to the router. What is the very first thing that that router is going to do with that frame?
Take the destination IP address?
Nope, not yet. You're right. It is going to look at the destination IP, but you go to the mailbox, you pick out all the letters from the mailbox. What's the first thing that you do when you open the mailbox? You're looking for letters that are addressed to you. So the first thing the router is going to do is look at the layer 2 header and say, is this letter for me? Based on that destination MAC address, the router says, oh, this letter is for me. So it's going to open up the envelope, which is the layer 2 header. It's going to throw away the envelope, so layer 2 goes away. Then looks at the destination IP and makes a routing decision, okay? That's what we see in the second part of this, or the next slide. So now the frame has arrived at router 1, and it identified that the destination is 4.10. So it looks at its routing table and says, do I have a route for the 4.10 subnet? And the 4.0 subnet is 2 hops away, and the packet needs to go to 2.2. That is called the next hop IP. Remember, the goal of a router is not to send the packet to its destination. The goal of a router is to get the packet to the next router, based on where the destination exists. Does that make sense? But here's the problem. We threw away the envelope. So before I can actually send that datagram over to router 2, what do I have to do with the data? I have to put it back into an envelope. Layer 2 was stripped off coming on the ingress side. Layer 2 needs to be re-added before I send the data on its way. What is the source MAC address of the frame at this point? It's the egress interface of the router. What is the destination MAC? It's the ingress interface of the next router. Isn't that where layer 2 begins and ends? Right? Every time you go through a router, layer 2 gets completely removed and then gets recreated when the data gets sent out. Now, in this particular example, we were going from Ethernet to Ethernet. So the envelope that came in is similar to the envelope that's going out. So now I send that on the wire, goes over to router 2. What's the first thing that router 2 is going to do? It's going to look at the envelope and say, is this for me? And 0B31, hey, that's addressed to me. So it's going to strip off the envelope. It's going to look at the destination IP, and just like before, it's going to check its routing table and says, oh, I have a destination route for the 4 subnet. It's now only 1 hop away. I need to go to 3.2, which is the next router. How do I get to 3.2? I go out of my serial 000 interface. But what has to happen before I send that data out of the serial 000 interface? I have to put it back into an envelope. The only difference, we call that encapsulation, yes, absolutely. The only difference in this case now is that it's not an Ethernet envelope, it is a HDLC envelope or a PPP envelope. All right? We'll call it a PPP envelope. Notice that we don't have like a destination MAC and a source MAC because it is a point-to-point circuit. The only place it can come from is whoever sent it, and the only place it can go to is whoever's receiving it. Make sense? All right, great. Router 3 receives the envelope. What's the first thing it does? Is it for me? Well, this happens to be this is for anybody that receives it, so the router says, okay, I'll open the envelope. Guess what the router does? Looks at the destination IP, looks at its routing table and says, oh, the 4.0 subnet is directly connected to Fast Ethernet 00. Before router 3 can send that information on to PC2, what does router 3 have to do with the payload? Has to put it back into another envelope. Make sense? What kind of envelope are we putting it into this time? An Ethernet envelope. What is the source MAC address of that envelope? Well, it's coming from the router. What is the destination MAC? The PC.
So now in R1, R2, and R3, or the relationship between R1 and R2, or R2 and R3, so it has to have a layer to switch in it to do the connection.
Not necessarily. The question was, the relationship between R1 and R2 has to have a layer 2 switch in it? No, you can plug these routers directly into each other. That's perfectly allowed. You could have a switch in between, but that brings up a good question. What if I do have a switch in between? Does it change the framing? Does it change the encapsulation? If I put a switch between router 3 and the PC, if I put a switch between the router 3 and the PC, does that change anything? And the answer is no. The switch is never the destination. Remember what I said yesterday about switches. Switches are transparent to this whole process. When the router knows that the destination is attached to an interface that it's connected to, the router could care less if there are 5 switches or 10 switches in between. It's still going to ARP for the MAC address of the PC. Because the switches use the MAC address to forward frames, but the switch is never the actual destination. So to reiterate what you were saying, just because it's Ethernet, I could plug a PC directly into a router. I can plug routers directly into each other. Just because it's an Ethernet link doesn't mean that there has to be a switch there. However, it wouldn't really matter if there was.
Actually, I have another question.
Sure.
Within the router, what does do the layer 2, which is identify the source MAC and the destination MAC?
The router has that intelligence built in.
Okay.
The interfaces themselves, you know, routers operate at layer 3, but that doesn't mean they don't have a physical layer component or a data link layer component. They clearly have a physical layer component. They have interfaces, right? And let's say they have Ethernet interfaces. Those Ethernet interfaces have MAC addresses.
So it's like the switch, it has its own database and write down the MAC addresses of the devices that
Yes,
are connected to.
exactly. It keeps its own ARP cache. Routers send out ARP requests just like a PC does. Routers have their own ARP cache. They have their own, they don't have a MAC address table per se because they don't really care about forwarding frames, right? MAC address tables are used by switches to make decisions on forwarding frames. But routers have something similar, don't they? It's called a routing table. Routing tables are what routers use to make their forwarding decisions, right? So this hopefully kind of sheds the light a little bit on how to troubleshoot, right? If you're thinking about data flowing through a network, and I'm going to be giving you these kind of tidbits throughout the rest of the week, but if you're thinking about data flowing through the network, don't you think it's kind of important to understand how this data gets manipulated as it flows from one point of the network to the other? Absolutely. Absolutely. All right. Now, there is the possibility that IP addresses could change as well. In what scenario would IP addresses be changed? There's really only one. If you're doing some sort of network address translation. We're not doing that in this case, so we don't see layer 3 change. So generally speaking, here's the rule that I tell everybody. Every time you go through a router, layer 2 changes, but layer 3 stays the same. Obviously, the exception would be if you're doing some sort of network address translation. All right? So guess what? We are now going to build a network. We are going to build this network. And I'm actually going to give you guys a little bit more time on this than I normally would, because this particular topology, you definitely want to save this when you're done. We're going to be using this topology for the rest of today and even into tomorrow. All right? So it's very important that, that you keep this, all right? Before we start building this network, I really need to kind of walk you through on a few things here, all right? First of all, this is the exact same topology that we just described when we were talking about the introduction of routing. We have 5 subnets, right? 1 subnet, 2 subnets, 3 subnets. Even though there's only 2 devices on that network, it's still a separate network. 4 subnets and 5 subnets. So basically what we can say here is that we have 5 broadcast domains. 5 broadcast domains. Okay? If a PC over here on the left sends a broadcast, it stops at that router. All right? So what we're going to do is we're going to build this topology, and we're going to use this topology to understand the concept of routing, and also we're going to configure static routing on this network. We're going to do things like route summarization. We're also going to be doing RIP routing. We're going to be setting up RIP and actually configuring RIP routing on this network. All right? Take a look at router number 1. Everybody look at the screen here and take a look at router number 1, because you guys will get confused. Everybody that does this class, they get confused about this concept because we're doing something a little bit out of order here. We haven't talked about subnetting. We haven't talked about subnet masks. We haven't talked about the makeup of a network. But I want to be very clear. The addresses that you see listed on this topology diagram, these are the network IDs, meaning we don't assign those addresses to interfaces. Those are just the addresses that represent the network. Okay? Just keep that in mind. We're going to talk all about network IDs and broadcast IDs and all aspects of IP addressing in the next chapter, but just keep that in mind, number 1. Number 2, I made a few notes on here. The routers are 2911s. The switches are 2960s. Okay? All router LAN interfaces. When I say all router LAN interfaces, what do I mean? What is a LAN? We talked about that on day 1. It's the Ethernet networks, right? All LAN interfaces are .1 in their respective subnets. What do I mean by that? All router LAN interfaces are .1.
So the IP that is like 0 on router 192.168.10.1.
Right.
The first object is 1.
Right. The IP address on this interface here, gig 00, is going to be 192.168.10.1. The IP address on this interface, gig 01, 192.168.11.1. The address on this interface, 10.1.1.1. The address on this interface, 10.1.2.1. Does that make sense? What about the serial link? Well, that's already drawn here. 225 for that side, 226 for that side. Joe D had a question. Will we cover how broadcasts are done in IPv6? Yes, I will talk about that. Absolutely. In the next chapter, we're going to be getting into much more depth on addressing and addressing architectures, and we'll talk about broadcasting in IPv6. Okay? For this topology, the other thing that I want to mention, what about the PCs themselves? What about the PCs themselves? What addresses are we giving to the computers? All hosts are .10 in their respective subnet. All hosts are .10. By the way, this is not a lab that you'd see on the test. I get that question a lot. Is this something I'm going to have to do on the test? No, this is way more difficult than what you're going to see on the exam. All right? And it's actually not that difficult. This is the fun part. This is where we actually get to really build a real network. Okay? To which interfaces are connected the PCs and the links from the router? No, you would not see this in the exam. There are no configuration labs in the split exams. Only verification labs. The switches, let's talk about that because that'll answer Gio's question. The switches are kind of transparent here. We don't care about what happens with the switches. I don't care what interfaces you use. We're not putting IP addresses on the switches. We're not doing VLANs. So no configuration on the switches at all. Okay? So before I cut you guys loose to start doing this configuration, And this is the first lab where I'm actually going to have you do it on your own, and then we'll do it together after you guys have started, is to how to get the serial connection between these routers. Let me show you how that's done in Packet Tracer, because those routers don't have serial interfaces by default. By the way, please, please, please make sure that you use the right interfaces when you're connecting everything. Otherwise, all of your outputs will be different than what we see in the lecture. If you're using different interfaces, it's not going to match up. Okay? So I'm just going to show you the router part right now, and then I'll give you guys a chance to kind of build this out. So 2911 routers, so we're going to pick our 2911, drop one in, and then I'll drop the other one in. As far as the name of the router, it doesn't matter what they're called. Well, in my case, router 5 and router 6, because I've been using this for a while. When you click on the router, if you want to add interfaces to a router in Packet Tracer, you click on the router, and interestingly enough, the first thing that you have to do is you have to turn off the router. There's actually a power button on the router that you have to click. When you see the display of the router, when you open it, there's a power button that you actually have to click. Let's talk about this router for a second. This is the business end of the router. What you're seeing here with the slots, this is the pretty end of the router, right? You've got your power cord, you got your power, and you've got underneath this faceplate is a DC receptacle for DC power for redundancy. You got a couple of network module slots, and these little black squares that you see here, these are WAN interface card slots. We can put different types of cards. You see the yellow squares? Those represent my gigabit Ethernet interfaces, and I have my console and my auxiliary port. On the left side, you see the modules that are supported. HWIC2T is a 2-port serial card. So I'm just going to simply drag that over, drop it into the slot. Now I've added 2 serial interfaces to my router. Turn it on, and do the same thing for the other router on the other side. You have to turn the router off, drag the card over, drop it in, turn the router on. All right? Then you just drag in your switches. 1, 2, 3. Where'd it go? I got all kinds of stuff on this diagram. 3. Let's get rid of those. And 4. All right? As far as connecting everything together, we need our PCs as well. So 1 PC, 2 PCs, and 3 PCs, and 4 PCs. And then you can move them around. All right? Grab your cabling tool. Let's go ahead and connect our PCs. As I said before, it doesn't matter what port on the switch you connect the PC to, because we're not configuring the switch, so we don't care about that. But when you're connecting the switch to the router, make sure you use the right port. Gig 00 for the top switch, gig 01 for the bottom switch. And on the serial side, the red lightning bolt, serial 000 to serial 000, and the same thing on the other side. So I'm going to give you guys about 60 seconds to go ahead and get your physical topology set up real quick. Don't start doing any configurations yet. I mean, I guess you could if you know what you're doing, but I just want to kind of walk you through that before I actually cut you guys loose to do the configurations. All right? So I'll give you guys about 60 seconds to get your physical topology set up, and then we'll continue on and talk about what your actual configuration task is. Now that you have all your physical layer connections done, your task is to configure these routers with their basic configuration. The only configuration that I want you to apply, I don't want you to do any routing. You guys, some people may have understanding of how OSPF works or EIGRP or static routes. We're not doing any routing yet. Your only task is two things. Assign all of the IP addresses to the interfaces and turn the interfaces on, and assign all of the IP address information to your PCs. Remember, the PCs also need a gateway, because if you want to be able to talk outside of your subnet, you need a gateway. What I did on the slide here is I gave you an example of the steps that you would take to do this configuration. This is not the entire configuration. What you see on the screen here, it's just an example of the configuration. All right? So for example, on router 1, you go into global configuration mode. Watch up on the screen first before you start doing it. I want to make sure you understand the steps before we actually, because then you get a little bit lost. And all right? Go into the interface that you want to configure. Give it an IP address and a mask, and most importantly, turn it on. You're going to do this step 3 times on router 1. You'll do that step 3 times on router 2. Make sense? And then on the PCs, of course, each PC you need to assign IP address, subnet mask, and gateway. Okay? So now I'm going to give you guys about 15 minutes or so to do all that configuration. And then we're going to go together as a group to verify that it's correct before we move on to our next step. All right, so about 15 minutes or so to complete that part of the configuration. I want to walk through the configuration step by step here. I know that you guys have been doing this configuration for the past 15 minutes or so. But, you know, I also understand that some of you may be seeing this for the very first time, and you've never done this before. Sometimes I have to teach myself to think that way, because obviously I've been doing this for a very long time, and things that seem basic to me are not necessarily basic to everybody else. So what I will do is I will kind of walk through, really, I'll do router 1 first, then I'll do router 2, I'll configure my PCs, and hopefully for those that haven't quite finished, you can kind of follow along and catch up a little bit, okay? So I'm going to go into router number, well, the router on the left, we'll call it router 1. And you'll notice when I open up the command line here, it says continue with the configuration dialog. This is what we call the setup. The reason why this shows up, and this is what you got stuck in, the reason why this shows up is because the router didn't have a configuration. All right, there's nothing in that dialog that's useful, so I'm going to get out of there and I'm going to go into privilege mode. The first thing I'm going to do, I didn't ask you guys to do this, but the first thing I'm going to do is I'm going to name my router. Why? Because I want to know which router I'm in when I'm doing my configurations. I don't care what you name it, as long as you know the difference. All right? So I'm going to go ahead and assign the IP address to the gig00 interface. So I type interface gig 0/0. That takes me into the interface that I want to configure. Notice my prompt changed to config-if. I am now going to assign an IP address to this interface. It is 192.168.10.1 with a subnet mask of 255.255.255.0. Lastly, I'm going to do a no shutdown to turn on that interface. Now that interface comes right up because there's a switch connected to it, right? Now I can switch directly to the other interface. Notice I use the abbreviated version of the command, INTGI01. GI is just an abbreviation for Gigabit Ethernet. There are no other interfaces on this router that start with the letters GI. So it knows that I'm talking about gigabit. Ethernet would be E. Fast Ethernet would be F. Serial would be S. That make sense?
Yeah. But it doesn't work in packet trace,
Sure.
abbreviation?
Sure it does. If you put enough characters to make it unique. I'm using packet tracer. I just did the abbreviation. All right. IP address, 192.168.11.1, 255.255.0, no shut. Interface serial 000. See, I can use the abbreviation. IP address 209.165.200.125. Let me just confirm that. 225, sorry. 209.165.200.225 with a mask of 255.255.255.224. Actually, that was going to be 252, sorry. By the way, we're going to learn all about what that means in the next chapter. This concept of subnet mask. Very, very important concept when it comes to networking. Do a no shut. Notice that interface didn't come up because the device on the other side of that interface is not configured. So let me just do my configuration on my router on the right real quick. Oops, I disconnected my cable. Nope. Config T interface gig 00, IP address 10.1, 1.1, 255.255.255.0, no shut, interface GI01, IP address 10.1.2.1, 255.255.255.0, no shut, interface serial 000, IP address 209.165.200.226, 255, What
happened with me right now?
Yeah, I can't type. I can't type for some reason. All right. All right. I did that second router rather quickly because I figured you guys probably had a really good idea of the steps that I was doing. All right. Now let me just configure my PCs. I click on the PC. I go to my desktop tab, IP configuration. All of the PCs are .10 in their respective subnets, and the gateway is the router that they're connected to. All right. Let's do this PC. (192.168.11.1). There's no save, you just close it, and we'll do this PC. This guy is 10.1.1.10, 255.255.255.0, 10.1.1.1, and this PC here, 10.1.2.10, 255.255.255.0, 10.1.2.1. Okay. Now, this is where we really get to understand what we're doing, because now we get to verify if we did it correctly. And if you guys didn't do it correctly, you're going to find out here pretty soon. Oops, I forgot to name my other router. I'll do that in a little bit. Remember that command I told you guys about yesterday? Show IP interface brief. Show IP interface brief. Let's all go into router number 1 and run the command show IP interface brief. Let me make my screen a little bit bigger. Show IP interface brief and verify our configuration. What you have on your router should match exactly what you see on the screen. Gig 00 should have an address of 10.1, and it should have a status of up. Did you get the command, sir? Right here. Show IP interface brief. I abbreviated the command, but Remember, this is the Phillips head in your tool chest. This is the tool that you use every single day. Show IP interface brief. Got it? Are you in configuration mode? You need to put a do in front of the command if you're in configuration mode. Okay? Or you can simply get out of configuration mode by typing end. All right? Gigabit Ethernet 00, IP address of 192.168.10.1, status of up. Remember what the status represents? Physical layer. Protocol represents the data link layer. So it looks like that interface is working. Gig 01, IP address of 192.168.11.1, status up, protocol up. Serial 000. 209, make sure you didn't type fat finger the numbers here because this happens a lot. 209, 165, 200, 225. Is yours correct, sir?
No, I didn't configure my serial.
Okay, well, there are interfaces on our topology. The routers have to talk to each other, don't they?
Yeah.
How are the routers going to talk to each other if the serial interfaces don't have IP addresses? Look at the topology diagram. This is a network, isn't it?
Mm-hmm.
Doesn't it have to be configured?
It has to, yeah.
Okay. So you need to go into your serial interface, config T, interface serial 000, give it an IP address and a mask. Look at your topology diagram and configure it based on the topology diagram. All right. Now I see up here because I've configured both sides of the link. Physical layer is up, the data link layer is up. Need some assistance, sir?
Yeah, I'm trying to find a command to configure the serial.
It's the exact same process as Gigabit Ethernet. The only difference, okay, listen for a second. Go into configuration mode, just like you normally do. But instead of typing interface Gigabit Ethernet 00,
You're going to need serial.
interface serial 000, just like what you see in the diagram. And then you give it an IP address and a subnet mask, and you do a no shutdown. All right? Okay? Let me know if you get hung up over there. We have some other interfaces here. We're not using these interfaces. For example, Gig 02, notice that it's administratively down. Same with Serial 001, administratively down, because we're not using those interfaces. The data link layer is up. The physical layer is up. All right? So I can actually ping from my router to my host. If I configured my host correctly, I should be able to get a reply from pinging my host. Why did the first ping fail? Because the router is doing its resolution. If I do a show ARP, I can actually see the ARP cache, and I can see the entry for 10.10. You guys remember what I said about the dashes in the previous chapters? I said the dash means what? What does the dash mean? That this is local to the router. Yes, sir.
No, actually, I did it. I was like, yeah. I'm looking trying to get out what you just said, but I did it.
Yeah, no problem. You did 225?
Yes, 225, 225, 225.
No. The IP address. What IP address did you assign to the serial interface?
209.165.200.226.
Are you on the right router or the left router?
That's the left router.
The left router is 225.
Left router 225.
You see that on the diagram?
I was looking at here. Okay, sure. I can redo it right now.
Okay, and then you still have to configure the other router too. All right? All right, what if we want to deassign an IP address? Yeah, essentially you do the exact same command, but put a no in front of it. All right, or for IPv4, you can't do this with IPv6, but for IPv4, you just simply put the address in again and it will replace it. You don't actually have to remove it, you can just simply reissue it. All right, I can go ahead and ping on my PC here. I'll go ahead and ping, I'm in my router, 192.168.11.10. Make sure I can get to that host. All right. And I can ping those PCs no problem because they're directly connected. The PCs are directly connected. I will not be able to ping the other PCs, but we'll talk about that in a second. All right. I should even be able to ping the router on the serial link, 209.165.200.226. And sure enough, I can ping. Wait a minute, I didn't lose a packet. I lost a packet when I pinged PC1. I lost a packet when I pinged PC2, but I didn't lose a packet when I pinged the other router. Why not? Think about it for a second, guys. Why did we lose the packets for PC1 and PC2? We lost the packets for PC1 and PC2 because of ARP. And what is the purpose of ARP? To map a MAC address to an IP. What type of link do I use to go to router 2? Serial. There is no MAC address. There is no ARP. Make sense? Right? There is a layer 2 address. It's just a well-known broadcast address for HDLC. HDLC is the default encapsulation for our serial links in Cisco. All right? Let's go ahead and check router 2. Make sure router 2 is configured correctly. We're going to do the same process. I'm going to give my router 2 a host name. I forgot to do that before. Show IP interface brief on router 2. Now, I pretty much have already figured that most of it's configured correctly because I was doing pings to test everything. Show IP interface brief on router 2. Go ahead and run it. Did you run it, sir?
Yes, I got it.
All right, and your screen matches my screen?
Exactly.
10.1.1.1, 10.1.2.1, 209.165, 200, 226. Excellent. Okay. Now I have a couple of questions for you guys. If I'm looking at this diagram here, we've kind of verified that all of our addresses are set up correctly. I haven't really verified that your PCs are set up correctly, but we will find that out in a little bit. Should PC1 be able to ping PC2 with the configuration that we have?
Yes.
Okay. Well, this is the reason I asked this question, because, let me see, give us, for Cisco security. Let's get through this class first, and then we'll talk about other classes, all right? All right? Yes, let's get through this class first. Okay. The question posed was, can I ping from PC1 to PC2? Well, here's the way that you need to think about this. Okay? Here's how you need to think about this. Put yourself in the network like you're the packet. PC1 needs to ping PC2. Is PC2 on the same subnet? PC2 is on a different network, isn't it? It's on the 11 network, and PC1 is on the 10 network. So what is PC1 going to use to be able to get to PC2? It's going to use its default gateway. Agreed? Did we configure default gateways on our PCs? Absolutely. So the default gateway on PC1 means no matter where PC1 tries to go, it's always going to send its packet to the router. Yes?
Yeah.
This is the default gateway, isn't it?
Yes.
Now, the question is, does router 1 know how to reach PC2? Does router 1 know how to reach PC2?
Yes, it does.
Yes, it does, because it is directly connected. That's one of those C routes that we talked about. We're going to see more about that in a little bit. But PC2 is directly connected to the router, so the packet will go over to PC2. But getting the packet in one direction doesn't always mean the packet can go back in the other direction. Do you follow what I'm saying?
Mm-hmm.
If I send a ping, I hope to get a response. Does PC2 know how to reach PC1?
Through the default gateway.
It uses a default gateway, which goes back to the router. Does the router know how to reach PC1?
Yes.
Yes, because it's a connected route. So, PC1 can ping PC2. And vice versa. Let's go ahead and test it, because I want to make sure that your guys' default gateways are set up correctly. I'm going to ping from PC1 over to PC number 2, and I get replies. All right? This is what I'm talking about when we talk about everything in routing happens piece by piece by piece by piece. If the default gateways aren't configured correctly, your ping stops at that point. Did your ping work?
Yes.
All right. All right, let's continue on then. Does PC1 know how to ping 225? Does PC1 know how to get to 225? Well, it's the same logic. PC1 has a gateway, which sends the packet to the router. Does the router know how to get to 225? Of course. 225 is connected.
Mm-hmm.
Does the router know how to get back to PC1?
Of course.
Yes. So that ping will work.
So in this case, PC1 can ping also the router on the right.
Well, let's talk about that. Okay? The question was, can PC1 ping 226? We already know that router 1 can ping 226. Why? Because that's one of those connected routes. These routers can ping back and forth because they're directly connected to each other. So logically speaking, you might go ahead and say, well, if router 1 can ping 226, and if PC1 can ping router 1, then it makes sense to say, well, PC1 should be able to ping 226. But follow the logic. We know that the packet is going to get to the gateway. We know that router 1 knows how to reach 226 because that's a directly connected route. But at that point, the ping fails. Why? Router 2 needs to respond to who?
PC1.
To PC1. Does router 2 know how to reach PC1?
No, because they're not on the same
It's not connected,
It's not connected here.
and we haven't set up any routing, so the ping will get to router 2, but it won't go back. Which, by the way, is the same logic, PC1 getting over to PC3. The difference is, well, let me ask you, where would the ping fail if I'm going from PC1 to PC3? If I'm going from PC1 to PC3, where would the ping fail?
It will fail by the router on the right side.
It'll fail on router 1.
1?
Yep. Because router 1 doesn't know how to get to PC3.
Oh, okay. So
I'm trying to go from PC1 to PC3.
we're going to go back and stop here.
It won't even go out. Because router 1 is going to say, okay, you want to send a packet to 10.1.1.10? I have no idea where 10.1.1.10 is.
Oh, even when it's not going to at all.
No, because it doesn't know where 10.1.1.2 is, or 10.1.1.10, excuse me. See, that's the thing about routers. Routers don't do anything unless you tell them to. Unlike a switch, which floods information, we can't assume that the packet goes to router 2. We can see the topology with our eyes, but the router doesn't know what the topology looks like. The router simply looks at its routing table and it says, do I have a route for that destination? If I don't have a route for that destination, then I'm going to drop the packet. Okay? Which, by the way, we're going to look at routes here in a minute. Show IP interface brief, we already talked about that. We did a couple of ping tests. We noticed that the pings didn't fail on the serial link because guess what? You know now pings fail initially because of ARP, and you know that ARP doesn't run on serial links because there's no MAC addresses on serial links. It's amazing how all this stuff kind of fits together. We're building the foundation of your knowledge so that you can deduce things about the network because of that foundation. All right? So let's go into router 1 and let's look at the routing table. This is the first time that we're going to investigate the logic that the router uses to route. We use the command show IP route. All right. Now what's interesting is that you see a bunch of codes here to indicate a lot of different types of routes. But in reality, there are only 5 routing protocols that exist. EIGRP, there's a couple of different types of EIGRP routes. OSPF, a lot of different types of OSPF routes. EGP, I'm surprised that's in there. That routing protocol has been retired long ago. This protocol we don't like to talk about too much anymore. And we have RIP and BGP. All right, now we're going to get into a lot of these other routing protocols. In fact, we're going to do RIP, we're going to do OSPF, we're going to do EIGRP, and we're going to take a look at BGP. All right? But we don't care about those yet. Let's focus on the ones that are the most important. Connected routes. All right? How do I read a routing table? And by the way, this pretty much works the same way on all routers. The formatting might be slightly different, but the concept is always going to be the same regardless of the router type. Anything that has a code next to it is an actual route. So actually, if you look at this table, we have 6 routes in the table. 6 routes. 3 connected routes and 3 local routes. Okay? We know what a connected route is. A connected route is a subnet that is directly connected to the router. We can see here that 192.168.10.0 is directly connected to Gigabit Ethernet 0.0. 192.168.11.0/24 is directly connected to Gigabit Ethernet 0.1, and the 209.165.200.224 subnet is directly connected to serial 000. Recently, though, within the last couple of years, Cisco started adding a second route to describe those connected interfaces. It's called a local route. The local routes and the connected routes are directly related to each other. One represents the network, the other represents the actual address on the interface for that network. So a local route is just the directly connected interface's IP address. Essentially, a local route is the same as a connected route. You can't have a local route without a connected route and vice versa. So in reality, on router 1, we really only have 3 routes. Okay? So you could do something like show IP route connected so that you could see all of your connected interfaces. You could do a show IP route local to see all your local routes. Of course, Packet Tracer doesn't do that, but you would be able to do that in the real world. This is the most important concept for a routing table. If the route does not exist here in any form, the packet gets dropped, period. If the route does not exist in this table in any form, then the packet gets dropped. Do I see a 10.1.1.0 subnet? No. Do I see a 10.1.2.0 subnet? No. All right? Any questions about that concept? All right? Of course, if we looked at router 2, we'd see a similar thing. We'd see routes in router 2. So there has to be a way to tell this router how to reach this network and this network. All right? There's got to be a way to tell router 1 how to reach those 2 networks. Well, that's what we're going to learn as well as we move through the next few chapters. All right? So we talked about what a connected route is. A represents how the route was learned. B represents the details of the route. C represents the interface that that route is connected to. We actually call that the exit interface. We call that the exit interface. Now, later on, we're going to learn all about how to set up dynamic routes. But dynamic routing table entries are not much different. You have a code that indicates how the route was learned, in this case with RIP. You have the destination network. You have how I get there. That is called the next hop IP address. And you have the interface that I go out of to reach that destination. Remember, routing is all about getting the packet to the next router. Or if it's a connected device, getting it directly to the device. Later on, we'll talk about what the 120 represents, what the 1 represents. I'm not going to talk about that right now because we're going to be configuring RIP in a couple of chapters here. If a route is not learned through the connected process, then it can only be learned through a dynamic or static process. Okay? That's the only 3 ways that you can learn about a route in a router. The route is either directly connected, it was learned through some sort of dynamic routing process, or it was learned through static routing. Okay? All right. Here's another example. This is an EIGRP route. Same concept. The code representing how the route was learned, the destination network, the numbers in the brackets that we'll talk about later, the next hop IP address, and the exit interface that I go out of to reach the next hop IP address. It's all about this number here. If I want to reach network 10.1.1.0, send the packet to 209, 165, 200, 226. All right, we have a few things to wrap up the chapter with, and then we'll take our afternoon break. Just like a switch, routers have different types of memory. They have RAM. By the way, save that file because we're going to be using that file later on. We're not going to be using it anytime soon, so you can close it out if you want, but make sure you save it, all right? We have RAM. RAM is our working memory. This is where our iOS runs, our running-config runs here, all of our tables and databases get constructed here, and so on. ROM, read-only memory, this is a chip that is inserted into a socket on the motherboard. You can kind of think, even though it's not quite the same, you can kind of think of ROM as your BIOS. It has limited boot information, okay? It has limited boot information, basically like a bootstrap code. It has limited iOS, and it has some basic diagnostic software. So if for some reason the router can't boot, or you have some corrupted files, at the minimum you'll be able to go into ROM, what we call ROM-mon mode, and you'll be able to recover that router platform or switch platform. All right. NVRAM, that is a partition of flash, and the only thing that goes into the NVRAM is your startup config, your boot configuration. Flash, that's your hard drive. That's what's going to store your iOS and any other system configuration files. These are the four major memory components of a switch and a router. I know it says on the screen router, but actually it's the same thing for a switch. We know that these routers have interfaces. This is a 1941 router, great little router. If you have a chance to pick up a couple of these online, they've got a switch port, switch module that you can put in. They've got a WAN interface card. You can swap different cards in there. And it's got a couple of LAN interfaces. Pretty good router. All right?
I have a question.
Yes.
So the internet provider will bring me the router and take from this router to our Cisco router then?
What do you mean? Like at your house or at a company?
At
or?
a company.
Okay, so the way it works at a company is typically the service provider, well, I guess I can kind of go through this discussion real quick. They're going to have a connection to your facility, okay? That connection goes into something called an MPOE, all right? That municipal point of entry, or the point of entry for your facility. If this is like a T1, which is a 1.544 megabit circuit, it's going to go into a jack on the wall called an NIU. That's a smart jack. It's used for loopback testing and for testing the circuit path from the central office to your business. Out of that NIU, you have an RJ48 cable, which goes into your router. That's your serial link that goes into the router. All right? Now, it doesn't have to be a T1. It could be fiber. It could be copper. It could be a cable modem or whatever. They're probably dropping bandwidth directly at your location. Some providers will put in their own equipment. Absolutely.
And then I will take like Ethernet J45
to their equipment, right.
From their equipment to my equipment.
A lot of times what a provider will do now, this happens quite a bit, they'll have some fiber coming into your facility, and then they'll have a MUX, what we call a multiplexer there, and that MUX breaks out two different connections. It breaks out voice and it breaks out data. It's called a hybrid circuit. So this is an Ethernet handoff. This is a PRI or a voice circuit handoff, and you run this data circuit to your router. You'll run the voice circuit to your phone system, and their equipment just takes those signals and converts them to packetized data and sends it over the fiber connection out to their central office. The amount of connectivity that's available to businesses today is a lot of options, right? You can even do wireless connections to a business. It doesn't even have to be a wired connection. But at some point, you're connecting to something physically. Make sense?
Makes sense.
All right. Now, this is the card. Actually, this is the router that we were using in Packet Tracer. This is our router. Remember the 4 slots that we saw? But what I want to point out is, remember I told you we were going to talk about this, is why is it 0, 0, 0? But in gig, it's 0, 1, 0, 0, 0, 2. Well, here's what the numbers represent. It might be hard to see on the screen here, but every one of these individual slots has a number. This is HWIC 0. This is HWIC 1. This is HWIC 2. This is HWIC 3. And then there's some modules here as well. This is the HWIC 2T card. That's actually physically what it looks like. And you'll notice it has serial 0 and serial 1. The numbering scheme basically represents where the card is installed and where the cable is plugged into. The first 0 is the whole chassis. The first 0 is the whole chassis. The second 0 is the slot that the card was put into. And the third 0 is the port on the card that you plug the cable into. So if I were to move this card over to this port, to this slot, and plug the cable into the top port, then that would be serial 0/2/1. Make sense? It changes for every platform, right? Every platform has a different configuration. So you have to look at the back of the device to see where the card is, how many ports are on the card, and so on. For example, this 1841 or 1941 that you see below here. Okay? This is HWIC 1. This is HWIC 0. So if I'm talking about this port right here, that would be Ethernet, because that's an Ethernet switch. What would be the first number?
0.
0 for the whole chassis. What would be the second number?
1.
1. And what would be the third number? Well, let's see. 0, 1, 2, 3, 4, 5, 6, 7. Make sense? Cisco starts their interface numbering at 0. That's why you see all these different kinds of numbers. The gigabit ports are fixed to the motherboard. They're fixed to the chassis. So 0 represents the chassis, and then 1 represents the port. This one right here is 1. 0, 0 is that one, and 0, 2 is that one. Does that make sense? All right. If I had a switch stack, remember we talked about switch stacks, right? 3 switches in the stack. There, I'll just draw my little stack cable here. All right. This is switch 1 in the stack, switch 2 in the stack, switch 3. So the fast Ethernet interfaces on this switch would be 1/0, meaning the chassis, and then the port would be the actual port number. Here would be 2/0, and then the port. Here would be 3/0, and then the port. In this case, the first number doesn't represent the chassis. It represents the switch in the stack. All right? It takes a little bit of getting used to this numbering architecture, but that's why you see different types of numbers for different interfaces. And by the way, you'll see TE, GI, FA, ET, SE. Those are the most common types of interfaces you're going to see. SE is what? Serial. ET is Ethernet, right? I'm not going to write them all out. FA is fast Ethernet. GI is gigabit Ethernet. TE is 10 gig Ethernet. All right? All right. We did talk about the boot up process for a switch. Well, guess what? It's the same process for a router. We do a post, which is our power on self-test. In a post, we're checking the hardware. We're making sure that all the interfaces are working, that the memory is working, that the motherboard is functional. We run our bootstrap code. Remember, the bootstrap has our bootloader commands, where we say boot system, and we can identify which iOSs to load. We look for the iOS in Flash. If the iOS doesn't exist in Flash, optionally we can configure to load iOS from TFTP. Once the iOS gets loaded, we start in Flash and it gets loaded to RAM. Then we go look for our startup config in NVRAM. If the startup config exists, we load that and that becomes the running config. If the startup config does not exist, we go into setup mode, which is that initial configuration dialog. All right? Same slides that we saw in the other chapter. Router boots up, we check the configuration register. If the configuration register is set to boot normally, we load the iOS. If there are boot commands, we follow what the boot commands say. If there are no boot commands, which iOS do I load? If I don't have any boot instructions, which iOS do I load first? If I have multiple copies of iOS in Flash, which iOS do I load first? The very first one that shows up, based on the name. When you do a dir flash, whichever image shows up first, that's the one it's going to load. Usually we don't try to keep more than one image in our flash anyway. All right? So that's what they mean by load the first image. They mean that I load literally the first image that shows up in the list. Then I load my config. If I can't find iOS in Flash, most likely I'm going to end up here. Remember, this TFTP boot option is not set up by default. That's something that you would have to configure for it to work. All right? Lastly, we do our startup config. Startup config is stored in NVRAM. If the config is there, it gets loaded and it becomes the running config. If there is no contents in NVRAM, if I don't have a startup config, then I will go to the initial configuration dialog. Another command that I want to point out here, and this is one of the very useful commands. I kind of talked about this command a little bit yesterday. Show version. We use this command all the time to verify our platform configuration. When I say platform configuration, I'm talking about what types of interfaces does it have? How much memory does it have? What is the iOS that it's using? What kind of licensing does it have, and so on. I can tell this router is running 15.2.4M1. Don't confuse, by the way, that iOS with this iOS. This is what's in ROM. That's my bootstrap code. 15.0.1RM15 is my bootstrap code. This is my iOS file location. This is the platform model. This is the amount of working memory that the platform has, the amount of DRAM. Add those numbers together, one is used and one is available. These are the types of interfaces that I have. This is how much flash and VRAM I have, and this is my licensing information. This particular router has the IP-based license, but it doesn't have the security license, and it doesn't have the advanced routing license. All right?
So typically with the version number, be exactly the same as the file name, or that's what's changed?
Yeah, you can rename files, right? But typically when you download iOS images from Cisco, the version is written directly into the file name. There's nothing wrong, as long as you don't change the extension, there's nothing wrong with renaming a file. But most people typically don't do that. They'll just leave it at the default name. All right, he's talking about this 1524M1 happens to be listed here. That's because the code version is written into the file name.
I have a question.
Yes.
Speaking of system administrator and IT, can we do as take an image of the iOS with the configuration as a backup in case the device dies, so I can buy the same exact one, just apply everything in 1 second, or do I have to go through everything? That's my question is for routers and switches.
Yes, so the question is, can I create backups of my iOS and my configuration if I have to replace the platform that I can copy those backups? The answer is yes, you can. We use TFTP for that, right? You can copy your iOS image off the platform, and you can copy your configuration off the platform. As long as the device that you're trying to install the configuration in the iOS on has the same memory configuration, has the same interface types, and is the same platform type, you can put that information back on the new platform. No problem, using TFTP. Now, that new router that you're installing everything on, most likely you're going to want to do some basic configuration manually. You don't want to be copying iOS images and configs over the console port. That will take forever. Remember, that console port's only 9.6 kilobits per second. Okay? So you'll probably at least, at the minimum, set up a temporary network between your PC and the router so that you can copy the files over the Ethernet interface instead of over the console serial interface. Right? But yes, to answer your question, creating backups and restores, we do that all the time.
So,
right?
So it would just be using like the kind of copywriting TFTP?
Yep.
I thought it wasn't possible to like copy onto the.
It is.
Oh, it is?
It is. However, when you're copying from TFTP to the running config, it's not going to turn on your interfaces automatically because it's merging the configurations. What you have to do is you have to copy your running config to flash, and then you do a command called configure replace. Configure replace would overwrite the contents of the DRAM. Right? It's possible to do a copy TFTP run. You can do copy TFTP run.
Yeah.
But whatever configuration is active on the router gets merged with the configuration you're copying. So if your interfaces are shut down, they're going to stay shut down.
Okay.
But if you copy your config from TFTP to flash, just give it a file name, and then you do configure replace flash : in that file name, then it replaces your running config completely. Does that make sense?
Yeah.
Okay.
Well, like coming back to what you said.
Sure.
When you just copy the iOS image and the running config.
Mm-hmm.
So we would let's say anytime you upgrade or change like the iOS image, you have to reboot the
when you copy the iOS image, yes, it doesn't. The iOS image doesn't load on the fly. You have to reboot the router for it to load that image. That's correct.
All right.
And be very careful when you're copying iOS because you may have enough flash to copy that iOS image, but you might not have enough RAM to run it. And if you run into that situation, the router just keeps rebooting. because it's trying to extract the image.
Yeah.
And if there's not enough space, it just stops and reboots and then tries to extract the image again, and it just keeps doing that over and over again.
That will lead me to another question. Does the flash and the RAM are upgradable?
Yes, on a router, flash and RAM are upgradable.
Mm-hmm.
On switches, unless they're a chassis type switch, like a 6500, most of your stackable switches, they have a fixed memory configuration. In other words, you can't really upgrade the flash or the DRAM because Cisco only puts out images that work with that particular configuration. So a 3750 or a 3850 switch, you can't upgrade the flash or the DRAM on those.
When you have let's say 3 switches that are stacked, is iOS running on all of them?
Yes.
Oh, okay, so it's not running on one end.
When switches are stacked together, they're all running iOS. They still have independent processors.
Oh, okay.
They just look virtually like one switch, but they still have local ASICs. They still have local memory buffers. They still have local processing that they perform, so they have to have an operating system. Okay? All righty, well that pretty much wraps up that chapter. Hopefully you feel like you learned a lot in that chapter. Obviously we still have a lot to do, but we're going to take our break and then we're going to move on to the next chapter.